So my name is Stéphane, and I'm here to present you the work we've done in creating a knowledge representation for neurosymbolic digital building twin querying. I'm affiliated to the Université de Bourgogne and to the company B27RA. I'd like to propose the following outline. So we'll begin with the context and research issue. Then we'll review existing approaches in knowledge modeling and knowledge-based query question answering. We then introduce our approach detailing the objectives, design, and implementation. In terms of relevance and speed, our results show significant improvements. However, we identified some limitations as well. And we will conclude by confirming the achievement of our objectives and outlining future work. So, to start with, as defined by ISO, BIM is the use of a shared digital representation of an asset to facilitate design, construction, and operation processes to form a reliable basis for decisions. This definition underscores the critical role of BIM in providing a unified and coherent digital framework that enhances collaboration and decision-making throughout the lifecycle of a building. An important component of BIM is the use of open standards for building representation. Among these, the industry foundation classes, also known as IFC, stand out as a pivotal element. These standards ensure that building data can be exchanged and used across different software applications and platforms, promoting interoperability and consistency in the industry. In recent years, there has been significant progress in integrating BIM with semantic web technologies. One notable advancement is the adaptation of IFC as an audible ontology known as IFC-all, as detailed by Powles and Turkaj in 2016. So the question we've tried to answer is, how can we harness natural language and semantic web technologies to ease query answering of IFC files? One example here is the following request. Find the exterior doors on the first floor with width larger than 1. There are 3 entities here: the first row, the door, and width, which means 2 hopes to go from start to finish. There is also a constraint on the doors in that they must be external, and the properties of the doors have numerical values, which requires handling numerical operations. In terms of related work, so developing our discussion of BIM and the IFC ontology, I would like to delve deeper into some of the challenges and adaptations in the knowledge representation models. The IFC ontology, as developed by Powles and Turkaj in 2016, as said, employs the all2DL format to offer highly expressive semantic representation of the IFC schema. However, this high expressiveness comes at a cost. The IFC data model, with its extensive structure comprising over 900 classes, poses significant challenges to reasoning engines, leading to very poor performance in practical applications. So to address these issues, recent efforts have focused on adapting the knowledge models to achieve a better balance between expressiveness and performance. Our approach involves using a less expressive structure akin to a custom RDFS schema. This simplification helps in reducing the computational complexity, thereby improving the execution of reasoning engines. A notable advancement in this context as well is the development of the IFC Natural Language Expression, or INLE, as presented by Yin and colleagues in 2023. INLE is an ontology that leverages natural language to enable more intuitive and accessible querying of IFC data. This natural language orientation allows users to interact with the building data in a more straightforward and user-friendly manner, further enhancing the usability and accessibility of the building information. Continuing on with our exploration of advanced techniques in the processing and utilization of building information, I would also like to highlight 3 pivotal areas of research for knowledge-based question answering. So the neurosymbolic reasoning, information retrieval, and semantic analysis. So firstly, neurosymbolic reasoning, as described by Zhang and colleagues in 2021, integrates symbolic and numeric AI to leverage the strength of both approaches. This hybrid methodology enhances the capability to handle complex reasoning tasks by combining the precision of symbolic AI with the learning abilities of numeric AI. This dual approach facilitates more robust and flexible problem-solving strategies, particularly beneficial in the context of complex building data. Moving on to information retrieval, Lan and colleagues in 2022 introduced a systematic approach to isolate and process relevant subgraphs from vast datasets. This structured method ensures precise and efficient retrieval of information from extensive and complex building datasets as well. And lastly, semantic analysis, as detailed by Yin and colleagues in 2023, focuses on the comprehensive understanding and processing of queries. This multi-step process ensures that the queries are accurately interpreted and effectively executed, leading to precise and contextually relevant results. Based on that, we build our approach. So let's now discuss the primary objectives of our research. First, interpretability. So one of the foremost objectives of this research is to ensure that the results are easily interpretable by the end users. This is crucial because the ultimate value of any data-driven approach lies in its ability to provide clear and understandable insights. Users must be able to comprehend and use the information without requiring extensive technical knowledge. Another critical goal is to maximize the reuse of existing ontologies. By building on established ontological frameworks, we can leverage the extensive work already done by the community, ensuring compatibility and reducing duplication of efforts. Furthermore, our research aims to create ontologies that the community can reuse. Customization is also a key objective. The approach must allow for specific expert as well as business subdomains to be considered. By accommodating these specific needs, the system becomes more relevant and valuable to a diverse range of users and applications. Finally, maintaining syntactic and semantic precision is critical, especially for constraints checking. Accurate syntax and semantics are essential for ensuring that data and queries are processed correctly and that the results are reliable. The overall system architecture is presented here. So I highlighted in green are the new elements added in this version compared to the previous one. So firstly, our new domain ontology that will be detailed a bit later. Secondly, a dependency and constituency tree is built for grounding query elements. This part will also be detailed further. So we decided to develop a new domain ontology that would complement the IFC ontology with input from domain experts to have a finer-grained description of the desired subdomains while keeping the ontology simple enough for existing reasoners to work effectively. So according to the 7-step methodology, we first determine our ontology's domain and scope. So for each domain, domain experts enumerate the important terms and structure them into a taxonomy built top-down from a single higher-level concept. They follow simple recommendations about naming conventions and guidelines regarding the expected structure. A group review of this taxonomy is then done to help the domain experts finalize them to ensure the level of detail is in line with our objectives and to check there are no duplicates of concepts across domains. The taxonomies are then processed automatically to fill the ontology. A manual review is done afterwards to check the consistency of the ontology, adapting it when needed while not deviating from the taxonomies. And as outlined in this 7-step methodology, the whole process is iterative. So still following that 7-step methodology, we identified the different ontologies we could reuse. IFC all is the most comprehensive ontology for IFC, which in our approach is complemented by INLE for handling natural language. As we create a new ontology, we maintain interoperability with IFC and INLE through unification for a faster and tighter alignment. To do so, we embed the shared meta model in our ontology. So we choose to proceed with alignment based on the internal structures of IFC and INLE, which allows greater control over the inferences in the context of global reasoning. Our work is easier because INLE has been built as an extension of IFC, therefore they are both already aligned. So for example, as illustrated here, based on the labeling rich beam done in a building model, the precise type of object from our ontology is retrieved for an individual that is otherwise typed as the broader IFC class IFC beam. This process allows us to add constraints of all kinds as material, dimension, position properties, and so on these individuals, enabling us to reach our goal for fine-grained description within the target subdomains. This graph illustrates the process of integrating an IFC model with natural language-oriented ontologies to build a natural language-enhanced model. The process is divided into three main stages: loading, merging, and building. Initially, we load the IFC model and its associated ontology. The IFC model provides a detailed representation of building information, while the ontology offers a structured framework for this data. Specific elements and relationships are then extracted from the IFC model to be utilized in the next stages. And next, we load ontologies that are specifically designed to handle natural language. So these ontologies include concepts and relationships that are useful for interpreting and processing natural language queries and data. Similar to the previous step, relevant elements from these natural language-oriented ontologies are loaded to be integrated with the IFC model. And then the extracted elements from the IFC model and the loaded natural language-oriented ontologies are merged. This step involves combining the structured data from the IFC model with the semantic capabilities of the natural language-oriented ontology. The integrated model is filled with additional necessary data and relationships to ensure it is comprehensive and functional. Any irrelevant or redundant information is filtered out to streamline the model. This model combines then the detailed building information from the IFC model with the interpretive power of the natural language ontologies, resulting in a robust system capable of handling complex queries and providing precise answers. The steps. So the first, the analysis step uses the user's question as input, triggering multiple natural language understanding analysis to obtain one dependency and one constituency tree combined into a single tree representing the whole query. Then the parse step traverses the dependency and constituency tree to recognize potential entities. It organizes them in branches of different length, following the overall structure of the input tree to generate an entity tree. This entity tree compresses all the possible branches between two entities. And then the ground step traverses the entity tree to look for the entities in the natural language knowledge graph, while also searching for potential links between such entities in this knowledge graph. These grounded entities and links, which are grounded triples, are stored in a tree structurally identical to the one of the entity tree, though lighter as some branches have been pruned in the process. The extract step explores the grounded triples, expands them in local Sparkle queries to be executed against the IFC knowledge graph, and ranks them against the triple score computed for the pruning in the previous step. The goal is to prune the grounded tree further. Each branch's best constraint, with which are triples grounded in the IFC knowledge graph, is then kept for the output list. The generate step stitches those constraints together in a shallow tree-like structure to account for the potential hierarchy of subqueries to form the final Sparkle query. Then the execute step executes the final Sparkle query against the IFC knowledge graph and collects the raw list of IFC results. The transform step passes the raw list of IFC results to obtain the labels and types of the objects from the digital building twin, so that very simple sentences can be created automatically using templates. These sentences can be presented to the user, though more importantly, they can be used in combination with the user's query for context to generate more complex sentences using pre-trained language models. Now let's talk about the results we've obtained. So the data set we have is made of 107 items across 22 questions. This is our ground truth. So as you can see, the recall jumped from 75% to 94% in version 1 to the latest version 2. We made the precision was lowered a little bit from almost 94% to 91%. And the F1 score, which is the harmonic mean of precision and recall, jumped from almost 84% to almost 93%. In terms of quality of the results, if we take the example of find the slabs in wood in a given building, so it was not working in V1, as wood can correspond to finish, to style, or material. In version 2, all possibilities are explored and grounded, so the correct slabs are found. This query took 0.67 seconds in version 1, and it took 1.79 seconds in version 2. The output presented then to the user was 0 item in version 1, which was not correct and not very user-friendly. There are eight items of type slab. These are with a list of objects in version 2, which is correct, but not very user-friendly. And there are 8 slabs made of wood in the building with a list of object IDs and some language around it in version 2 using PLM for generating the output, which is correct and more user-friendly. Out of the 107 items, 80 were found in version 1 and 101 in version 2. So we found way more stuff in version 2. In terms of speed to get those results, to load the models, it took about 30 seconds in version 1, and it's down to 18 seconds in version 2. And then to process the queries, it took on average 1 second in version 1, and the double, a little bit, slightly more than 2 seconds in version 2. So let's talk about the objectives. So really, I would like to discuss in detail how we have achieved our core objectives in this research. We ensure the system's results are easily understandable, offering clear explanations to make insights accessible to both technical and non-technical users. By leveraging existing ontologies, we enhance efficiency, ensure compatibility with other systems, and enable seamless data integration across applications. Our flexible design allows knowledge models to be tailored to various expert and business needs, providing relevant and impactful insights for different fields. We implemented rigorous methods for data accuracy and structure and meaning, crucial for tasks like constraint checking and validation, ensuring reliable information. So though through careful design and implementation, we have successfully achieved our objectives of interpretability, reusability, customization, and precision. To conclude this presentation, so I'd like to summarize the key improvements and future direction for our work. As you've seen, our latest version, as compared to the first one, has demonstrated significant improvements in both relevance and quality. One of the most notable achievements is an improvement in the F1 score by 9%. This enhancement is primarily attributed to advancements in our knowledge modeling techniques, which have allowed us to better capture and utilize the complexities of the data. But despite these advancements, there are several limitations we have identified. Firstly, the data sets we used was a bit too small, and we are unable to find a standard data set for our needs. This limits the generalizability and robustness of our findings. Secondly, our current parsing approach only handles straightforward logical relationships and ignores units by assuming the use of SI units. Additionally, we do not handle coreferences across sentences, which can impact the accuracy of our parsing. And lastly, the tree representation of our requests often becomes too broad and deep, making it computationally intensive. A full grounding against the knowledge graph also consumes a significant amount of time, affecting the overall speed of our system. So to address these limitations and further improve our system, we have outlined several areas for future work. First, we aim to develop and utilize a larger, more specialized data set that better represents the diversity and complexity of real-world data. Then implementing partial and smart grounding techniques can help reduce the computational load and improve efficiency. Also, by keeping the context of request, we aim to handle core references effectively, enhancing the accuracy of our parsing and interpretation. Additionally, aligning our system to more ontologies will provide finer granularity and a more comprehensive knowledge base. Lastly, we plan to optimize the use of natural language processing models to improve both speed and accuracy. So while we have made significant progress in enhancing the relevance and quality of our system, there are still areas that require further attention and development. By addressing the identified limitations and pursuing the outlined future work, we aim to create an even more robust, efficient, and accurate framework. So thank you for your time and attention. And if you have any questions or comments after that session, please feel free to reach out using the email displayed here.